Okay, well, let's see. So this is an unstructured section, and it's about machine learning for science, promises, and problems. So as you can see, something like very easy to summarize. It's not a lot of material at all. So I'm gonna see, like I've been brainstorming with myself essentially for the past couple of days, trying to think about, just some broad categories that we can build. And then I'm gonna ask you to give your input really based on, what's your everyday experience with, like doing research in machine learning to see what actually, are the things that affect us as a community, things that we are, proud of, and things that we feel need more work. So let's see, and I literally put them on paper. So I'm gonna try to have these like two boards of like the good things and the challenges. And, we are gonna start with the nice stuff. Right, so I'm gonna call this promises. Actually, I think I'm gonna say / achievements. Like in the sense that I feel like here, I'm trying to think and invite you to think, of course, with me, at something that we have already accomplished in a way, something for, like where we feel like, okay, we're excited about where we are. And then maybe later we can talk a bit more about, where do we want to be a little later on. So these are the good, actually. I'll make a flower too. Here. Okay, so let's see. The first one that I noted is perhaps not the most mind-blowing, but I still think is very useful, which is using machine learning to increase speed, right? So not doing something new or something that we couldn't do with other methods, but just doing it faster. And I think, because for all of us, we work in the universe, so we work with like very large data sets. And so sometimes being able to speed up things is good. So my first blob will be increase speed. I'm gonna make a little blob here. Okay, and in terms of, like what comes with this, I thought about, perhaps like, because I work with galaxies, I think, like the idea of automatic classification of galaxy morphology was like one of the first things that I was exposed to. And I still feel that, in general, like, automatic classification is a good example of things that we can do faster with machine learning, although not necessarily better. What else? Another thing that I think is important for us is anomaly detection. I think there's a lot of work being done in this. What does it have to do with speed? Well, these things are all interconnected, but I think, for a lot of upcoming surveys in astronomy, in particle physics, I think like the important part will have to be something with a very fast response time. And I think this is where these methods can come in. Another thing that I think maybe is like, dear to a cosmology crowd is using emulators. Right, so being able to use these techniques to, compute things like giant integrals or, forward modeling something very complicated with a somewhat simplified version that, once you have trained, you can actually generate in a very short amount of time. What else? Anything else that is dear to you that we think we can do faster? Don't worry, at some point I will literally force you. Yes, please go ahead.
I think there's also potentially interesting things in like calculatory inference and doing better MCMT sampling to try to guess proposal distributions and all these kinds of ideas.
Oh, very good, very good. I have a category with this that I have called optimization. So let me explain a bit more, and then you maybe can tell me whether you think like it belongs more here or there, because I feel like that's, like really something that deserves a bit of attention in itself. All right, so let me leave this one for now. And now let's see. Another thing that I wasn't quite sure of how to, summarize, but I called it increase flexibility. So here's another little bubble. And so here, I put things, for example, as working with higher level products, for example, using images versus catalogs. Something that in regular inference is very hard to do, but with machine learning we can do. And so I think this is, in my opinion, nice. So there's like images, there's sort of like, time domain data perhaps. Something that reduces the necessity of processing the data before we can actually learn from them. Because at each step, we usually have to simplify something, which means that there are some assumptions that we have to make. And so if we can take the data in one step before, I think is nice. I like to put in these categories also things like likelihood-free approaches. I'm saying approaches because, like, of course, we think about likelihood-free inference, but in general, like anytime we can sort of like have an alternative to forward modeling that doesn't explicitly requires writing a likelihood, this is something new that we can do. So just gonna leave it at that. And in this, of course, also, I think a special treat for this crowd includes learning from simulations. This is personally something that I'm very excited about, and I think it's one of the most promising avenues that we have. Yes, Rich?
Would dimensionality reduction go here?
Very good. I
Or
feel like
somewhere
I
else?
haven't even, why not? Let's put it there.
We can
here.
put it there.
Yes. I think dimensionality reduction will go in everywhere. It can go here. It can go here when we talk about, like I'll have the next category and then we'll see. What we think. Like, I feel like, yeah, it's difficult to, really classify all of these things. Then what's the next one? I was going between two things. One is reduced bias and the other is data-driven discovery. Oh, Shirley, yeah.
Figure out whether I should put higher dimensional mapping, learning higher dimensional mapping in either one of those, because it probably works for either one.
Higher dimension or lower dimension?
Higher dimensional mapping, right? From one map to another map.
Starting from a lower dimensional and going to higher dimensional, or
either way, it's just a mapping.
Oh, okay. Yeah. So. Yes.
That you mentioned, like for inference, that also relates to these faster simulations, but you can also learn the likelihood from a set of simulations.
Absolutely.
So there's many mapping that's going on. So I don't know where that should sit.
Yes, I think you're right. I mean, maybe something like this could be a floater. It definitely goes here. It can go here, and I think it will feed into something else as well. So let me tell you about what I thought, and I think will be relevant also for this, is, as I was saying, let me call them data-driven discoveries. And let me pick another color. And so here, for example, I would include things like automated feature selection, or more exciting perhaps, engineering. And so in a way, we can think about this as a form of dimensionality reduction and as a form of, like mapping from lower to higher dimension and vice versa. else do I have here? Anything that has to do with unsupervised learning. And something that we heard about earlier today, self-supervised learning. So I guess what I had in mind when I was thinking of this is something that has to do with examining the data to see what they tell us, but also something that it's possibly useful to check against our own biases and like being able to select variables that seem to be important for the process we're doing rather than choosing beforehand what they are. And another thing that I like about this is learning priors. And then, I guess I didn't. So this, I think, can feed also in here. Maybe I didn't quite divide my space well enough, but the last category, which I had, was optimization. And what I thought about like for this part is the idea, for example, of using techniques of like domain adaptation or transfer learning so that we can actually think about optimizing observation for things that we want to learn, like understanding where information is missing and what's the best way to go with it. And that's why I feel like, like also this part could feed into this optimization problem. And I'm sorry, I'm not sure I know your name, Wanda, perhaps? Yes, and so I feel like, like maybe your suggestion could also go in this part of, like just increasing efficiency when we plan how to get new knowledge. All right, so this is clear, like, very broad categories. Is there something we want to add to one or the other that you feel like it's important and exciting and is not yet featured, either as a category or as a thing? We're going to have more chances later, but do you think something is glaringly missing?
Sorry, could you explain what you mean by learning priors?
Oh, what I'm saying here is that, like, for example, when we try to do traditional inference, which is like model-based, let's say in cosmology, in astrophysics, and, we often do like Bayesian inference. And at least, like in my own field, which was learning about properties of galaxies, something that is missing is good priors on what distribution of these properties we are expecting. And so I feel like maybe something we can do with machine learning is to actually be able to learn these priors from data and then be able to reuse them to improve our traditional Bayesian inference techniques. All right, I see no objection, so let's get to the other side. Well, probably put this up. Okay, and it's down. And so here we have challenges. It's a color for challenge. Challenges. So we put the flower. So here, what are we going to put? I like it. It's a rain on our parade, but will not last for long. Okay, so I think the first item that I had here is interpretability. And make no mistake, I think even just at this workshop, we have learned, I think these are sort of like challenges, but maybe I should call it really work in progress. Because I think we are You are mostly. Really making great strides in all of them. But interpretability is something that, in general is, potentially worrisome, right? Compared to traditional inference methods, often we lose a little bit of transparency when we use machine learning. And so in this case, this is sort of like, what should I call? Scientific interpretability. But the other things that I worry about is sort of I don't know, like non-expert interpretability. What I'm saying is that, while I think, a lot of the scientific community and the astronomy community, can or used to be able to read most papers and understand the inference techniques that we were talking about. Well, something that I'm a little afraid of, and, like I wonder if you share this concern, is that, like a lot of people who are part of the community but are not trained in machine learning and deep learning in particular, may actually lose their ability to follow the literature. And so this is something that, like I've thought about, and perhaps is something that we should, think about and, like think how to tackle. And so this is, I don't know, I don't want to call it people interpretability, but it's more like, oh, perfect, yes. Very good, thank you. So this is something that has been on my mind. Another thing that I think, we talk about a lot is ground truthing. Which, to be honest, is a problem that we always had. We think about, so in general, I think it's just like more glaring when we talk about supervised learning algorithms, because we need some sort of ground truth to train them. And the ground truth for many things in the universe is just not available, or it relies on some simulations or some models. But I don't think this problem was absent before. Like every time we make a model, we only compare data and models in the context of that model. So if the model is not valid, our comparison is also not valid. So I don't think this is like a problem that is like inherent to machine learning in itself. But this is something that I think, we collectively think about a lot, right? Okay, like I've trained my model. Often I train my models on simulations. What would it take to believe that the model works on data as well? And so I think it's connected to, solving of the issues above, but in general is how can we trust models on data if they were built or trained using simulations, for example. Yes, please.
I think this problem kind of is related to the interpretability problem. Because, as you said, this has a long history. I mean, before machine learning, we also have this problem.
Yes.
But kind of the difference now is like in the past, because still people use some very simple mathematical tools. So they have kind of some checkpoints in between, right? If you see you have a set of simulations and you compare that to observations, and then you can check the performance of like particular statistics between them and see whether there's systematic error. But because now kind of the model or the inference machine of neural network becomes too big, so then it's usually hard to find some particular checkpoints and compare them. So I think this might be the difference now.
Yeah, no, I think that's very relevant, and I think this probably means that we need to build those checkpoints, right, to understand how to...
Yes, and but unfortunately now it's still lacking. Like many people realize, when we now want to check the kernel visually and see whether they're meaningful, usually they're not meaningful.
Right. Yeah, it's hard to understand what they mean.
Right. It would be very nice that if in the future we can have some checkpoint like this. We can check some parameters in the model, in the neural net, and then we can say this means something or that means something wrong.
Thank you. I think this is very important and relevant. Okay, another problem that I guess is connected is resources. And this so in part, this is sort of like, learning resources, but here I'm mostly talking about computation resources. So first is, is this a problem? And it's interesting. I feel like up to like 3 or 4 years ago, I would have said no. But now it seems to me that, just like how much we use deep learning has exploded. And so now my impression is that we are making use of a lot more resources. We need more resources. And I think, my other concern is, does this create, am I sure the answer is yes, does this create an equity concern? Like, I feel like, we have two issues. One is like, okay, like, do we need more resources than we collectively have? And then, like, once it happens, and I'm sure it will happen, then, like, just the distribution of these resources is not uniform in the community. What does it mean in terms of, like, who is able to access state-of-the-art research? So to me personally, this is a concern, but, like, I'd be curious to hear other opinions about, whether you anticipate this happening or whether you think it's a milder issue than what I'm thinking. And this is, like goes also back here, like to, like, are we creating access barrier by, like through this field that is developing so quickly? And this means that, like necessarily we leave some people behind. So what can we do to make this a little bit better? And I have to say, just, like as the last category of these challenges, I had things like, physics awareness or uncertainty estimation, so things that are a bit more technical. But I have to say, I'm not convinced they go in challenges anymore. I just feel like, in general, we heard a lot of talks, even the last couple of days. That seem to be addressing these issues. So, like, how do we infuse our knowledge of physics, things like symmetries and so on, into, our models? And, like, how do we, I think, we didn't used to talk about uncertainty estimation so much, and I think now it's more common, and, we seem to have a bit more of a framework. So I feel these are, I don't know. Overall, I would say, I don't know if these belong in challenges. So this is, the sort of like rough framework that I had. Again, do you see something that is glaringly missing from these challenges? Yes.
Would you please use your seat mic for everyone on Zoom? Let me just repeat. I think one of the problem of machine learning is sometimes accuracy. Usually, like given like a typical data set or typical time of training, a reasonable person will go on PyTorch and spend reasonable time training one network. Usually get to 1% level of prediction. You say, oh, it's good. Let's go home. But sometimes like precision requirement on science is like much more stringent. Sometimes it requires 10 to the negative 6% of requirement that you're not getting there with machine learning anytime soon. So
should we call this like evaluation in general? Because I feel like, another things that I thought about is that, as you mentioned, like sometimes, there is no clear benchmark. And sometimes just like the metrics that you sort of like, learn about in your classes are just not what's needed. And instead, we spend a lot of time thinking about what's a good evaluation metric for my problem. And so perhaps we can sort of like, this whole problem of learning what makes sense and then deciding what our goal is I think is important. So I'm going to write it as what's important / achievable. Yep.
This is somewhat related, but the idea of sort of no tests is quite important in like CMB analyses, and it's not immediately obvious to me how you can often incorporate that. So if I've trained a neural network to predict my cosmological parameters, how can I use that same thing in a no test framework to sort of test the data robustness in my analysis pipeline, if that makes sense?
Oh, can you tell me a little bit more? I'm sure I understood what's like no test.
Like
it's my ignorance, not your lack of clarity.
An example in the CMB community is we often take, I don't know, data taken on Monday and data taken on Tuesday and difference it and make sure that our pipeline returns things that are consistent with 0. So the power spectrum of the CMB should obviously be 0 there.
So sanity checks?
Yeah.
Building.
So the sort of built-in test that should be 0, and if they're failing is a sign that there's a problem in your analysis pipeline.
Almost like unit tests.
Yes.
Okay, I'm gonna.
But data consistency checks, kind of.
Right, consistency check. I think that's the. So I'm gonna just write that they are not obvious. Hopefully that captures this concern you had.
I think it's kind of related, and it's maybe not that much of a challenge, but I would say integrability in a pipeline. Like, okay, we develop a great tool, but how do you put it in a pipeline for the data analysis?
Yes, I think that's.
And it's very much related to consistency check, for instance, because, yeah.
Right, so let me put it over there so we can connect.
And there are already, like, for instance, emulators. They are kind of already well integrated, but I think there are many tools that we would need more work to get there.
Right, so I'm going to say interaction with other pipeline steps. And just put the connection between these. Yeah.
Another practical problem are hyperparameters. A lot of machine learning is hyperparameter tuning, and we also need methods to kind of know how sensitive we are to hyperparameter choices and maybe marginalize over them. So I think maybe this goes into uncertainty estimation, epistemic uncertainty.
Yes, I think it's true. And not just hyperparameters, but also choice of architecture, right? And all of these.
That's all of these like choices that one has to make, yeah. So it goes in there.
model. I'm just going to call it model choices, just to represent the fact that we're choosing a model, we're choosing hyperparameters, and you know, like this comes with its own uncertainties. Yeah.
We had this discussion yesterday, but it's hard to compare between the different papers, so because there's no common data set to compare against. So
Right. So should I put it here in terms of, you know, as part of our interpretability issue, that's sort of like literature?
Yeah.
Very cool. Yeah, surely.
To that, but it's reproducibility, right? So if someone produces a paper and then you have to reproduce the work, it could be a resource problem or patience problem. You just can't get it to work to that level. And then there's also this big problem, which we might not want to go into, is AI ethics. You know, stuff that we do might affect the real world applications in different ways.
Yes, I have it here in my paper. I have an ethics with a giant question mark because of this. That's why, you know, I sort of like, I decided to stay with, you know, I feel like the idea of equity. But yes, I think, you know, in the real world, it's a huge problem. And I can't imagine not becoming a problem for us at some point also, like even if the stakes are lower. But I don't think I got your first point about
right? So if you see a paper,
okay,
can you reproduce it?
Yes. And this is possibly connected to here. Like it's not a given that you will have the resources or the training, right? The necessary technical. Yeah, okay.
For computational resources, I was thinking about the balance between memory and computation usage. I think is going to be a big challenge. And then another one under that, connecting ethics and computational resources, is climate change. So people are starting to like put their carbon emissions of their big simulations on there, and that's going to get to be a big one.
And your first one was sort of like deciding or just balancing. So, oh, well, you know, there's also achievements. So it seems to be that collectively we are more focused on the next steps. But yes, you know, like you're welcome to, yeah.
Would you please use your seat mic?
Oh, yeah, yeah.
Yeah, so one problem from experience is maybe under evaluation is convergence. So
right.
Suppose you run a network on your problem and it doesn't do particularly well.
Mm-hmm.
You don't really know whether you just chose the wrong network or there's some inherent reason that your problem is not amenable to movement.
So yeah,
some kind of convergence question. How do you decide how to look for a better network for your problem?
So I guess this, I mean, you know, you could use like some diagnostics tools, but I would agree with you that sometimes even just, you know, usually you do some back of the envelope to say, okay, is this problem solvable? Is the information there? But it's not so clear that in this case we can do it. Does this, like, you know, if your method is not performing as well, how do you decide?
Yeah, I find little guidance. I find little guidance on whether you should keep trying for other networks.
Mm-hmm. Yes.
Or it's just there's no information to be captured.
Right. So let's see, how can we call this? Here I have what's important and achievable, and I guess this is related, but it's like, how do we pick a method, perhaps? Like just maybe like matching a problem to a method so that you know that you're trying what you should be trying as opposed to wasting time with something that may not work. Do you think that this is? Yeah.
Yeah, I think this is really interesting. I think this also relates to interpretability, but not the interpretability of results, but the interpretability of the neural network itself. The kind of now we again, I will repeat myself because many of the neural networks are developed not in science, but in other communities. Right. They have their particular purpose.
Right.
And also they have a lot of money, so they can basically try various different things. But now it seems actually very interesting. We can kind of have some mathematical understanding, or we perhaps we're starting to have some understanding of the neural network. Mm-hmm. And I think that will be very important as a guidance for scientists. It's right. Like the traditional machine learning tool, right? You have PCA, you have all yes. different things. And actually we understand what is the advantage of particular method, what's the disadvantage of when it will be proper. But now it seems for neural net, it's kind of a blind. So it will be very nice if in the future, kind of the research of neural network or the science of machine learning developed a lot, and then we can have this guidance.
Right. Yeah, I really like it. So I'm sort of mapping this as a sort of like interaction between these two things: the physics awareness, right? Sort of like like talking about the fact that we're solving a physics problems and how we can use this to guide our models, and then how that feedbacks again into the physics that we learn. Yeah.
I would say, like, related to the problem of how do we pick methods and like learning things from different communities. I don't know like how to exactly phrase it. Maybe human time resource mm-hmm. being a problem, because before, I guess, like you would try to maybe keep up an archive with the cosmology papers, but now with new methods being developed in other communities, like there is that sort of sociological pressure, I guess, in some sense, that to keep up with literature from other places as well. So that's sort of like, how much time do I dedicate to learning about like the state of the art in cosmology versus how much time do I spend learning things and like machine learning community, sort of like finding that balance.
Yes, and it seems to me that especially for younger researchers, sort of like, doing research in this field means that really you need to be aware of, like both like the physics and the computer science side, really at high level, which is, like I think a much more ambitious requirements than, what was the case like a decade ago. And so understanding, what this means for expectation, especially for junior researcher, I think is very important. Yeah.
Yeah, I want to comment a bit on the computational resources a little bit more. So I'm more of a machine learning person, but it seems to me that even though like the computational resources are increasing, like probably all the GPUs that we use in the room is a fraction of the cost of a space telescope. So in the grand scheme of like cosmology, the computational resources are not that expensive, and I'm hoping that funding agencies will see that theoreticians also need increased computational resources. But in the grand scheme of funding the project of cosmology or astrophysics, it's not, computational resources are much cheaper than building a telescope or sending a telescope in space. So hopefully, though there will be maybe some equity issues, funding, hopefully we should try to convince funding agencies to make funding generally available for these types of resources.
I think you're right. So I think if I understand correctly, what you're saying is this maybe like not a very dire need, but I think something that needs to be addressed. And again, I think this is something that is likely to be very unevenly distributed, unless as a community we make a targeted effort into like making this something where like there are some central resources that everybody can use.
Right, but what I'm saying is, even currently, right, I cannot go out and do a survey. That's completely out of the reach of my resources.
Sorry, where?
There's no way for me to go out and do a survey of CMBR, right? Some of the resources that we have for some of the things that we need are really very unevenly distributed because they're so expensive. They're hundreds of thousands times more expensive than the compute, which is the actually gathering of data.
I see. So what you're saying is like you don't feel that having access to computing resources is a major need.
No, I'm hoping that because it's such a small fraction of money, hopefully we can convince funding agencies to divert 1% of the money that they use to send space telescope into buying more GPUs, and that is enough for everyone in this room.
Right, but I guess what I'm, maybe I'm not able to interpret exactly your thought, but I think what I'm thinking is like, for example, a lot of data are public, like traditionally. And so, like say I'm a CUNY, like a CUNY student can, like go and, like run a project on this data. But, like once I need, once the barrier for doing interesting research moves to, okay, I need to have access to X computation resources. Now students like CUNY students are cut out. And this is, like where I feel like there is a concern. So I agree with you that it's not a huge need, but I feel like this is something where, I'm really scared of, how unevenly distributed it will be.
I guess in that case, maybe one way would be to look at different fields where their computational resources have been extensive for a long time. I'm thinking material science, for example, has been a field where they've been doing these kind of large-scale computations for a very long time, and they are supported by their funding agencies to buy this amount of compute power either through shared resources or specific resources, like all the exaflop projects and so on. All of those are reserved for these people. So maybe we should be going to the funding agencies are arguing that this is a very central part of research in cosmology in the future, and this is a funding necessity that really needs to be.
Right. Yeah. I think that's a great idea. They want to sort of like look at examples to see what can work for this. Paco, I think you had something, and then I'm gonna try and do something different.
Yeah. So for this, I actually have a kind of very strong opinion on this. So I did my PhD in Spain, and at that time I have like one laptop, and that's basically all I have. So when I came at CCA, I have this amazing cluster, right? And then there has been thousands and thousands of simulations. So I talked many times, for instance, with David Spiegel about this, right? This is not fair. It's not fair that there is one person that just because you have access to these computers, you are going to get all the credit just for this, right? This is not fair. So, but it's also not clear how exactly you can revert this. So, for instance, in my case, I always do everything public available. And I think Google, for instance, provides Google Colab, where you can have GPUs and all the resources. And it's a way to democratize this. But,
definitely, I use it a lot. And what I'm afraid of now is that, for example, now as you're ready to transition between the fact that you can use like a regular core, like kernel with a GPU and do okay. But I feel like, once you start, like the free plan is just like, not enough anymore. You're going to get disconnected, and then and this is where I am really afraid. I think this is something that, it's a big discussion. It's like, requiring, for example, NSF is, like financing all these like, new centers for AI, and, like demanding that, like part of these resources are shared and that access is given in a more equitable way. But yeah.
That I think some people on Zoom wanted to join the conversation.
Oh, I'm so sorry. Oh.
Yeah, can you hear me?
Sorry, yes.
I wasn't sure if I could just jump in or not.
Yeah, sorry about that.
Yeah, no worries.
Go ahead.
This is George Stein. Yeah, I definitely agree with this part on the equitability of computational resources. Because unless you do have access to, big disk space, a bunch of GPUs, you're really not going to be able to compete at, doing machine learning across a whole survey, hyperparameter changes, and all this stuff. So I do agree that this is an issue for, especially access for younger members. But I think there are some things that you've put on the top of the blackboard there that can help with this. And this is something we've been thinking a lot with representation learning. So traditionally, if you want to do, galaxy morphology across the whole survey, you need to store 100 million images you need to train some ResNet or something on these 100 million images, which is going to take hundreds or at least tens of GPU hours. And then you're going to need to, predict over this whole data set. But what you can do with representation learning is that you can kind of split up that process. So some group with a lot of GPU time and someone who wants to do this can go train a self-supervised network on 100 million galaxy images, taking 100 GPU hours. The self-supervised representations that you pull out, you kind of just can replace the data set. So instead of needing to store terabytes and terabytes of images, you just store these low representational vectors. And what you can do is just train very simple linear models that make predictions from these vectors. So through representation learning, you can, somebody's got to do it originally. Somebody's got to train these big models, but you can simply share the network, share the representations, and you can reduce this, multi GPUs, terabytes of disk space to something you can run on our laptop. Like the stuff we were showing in our work, it's you train on a CPU, just doing linear predictions from these representations. So I think there are avenues like this where you can start to collaborate and share, and maybe there's one master network that pulls out representations from the whole data set, and then you can take those and run with it with very minimal computational resources. So there's things like that I think can also be more used, just more collaboration with these things. Not everybody has to train their own network, on their own data set. We can start to just share representations, do these simple models, and make really cool scientific discoveries.
I think this is a really lovely thought, and just because it's 5, I really like the idea of sort of like ending with this positive note. I think this, like one thing that I will mention is that this goes back to, I really love your idea of, like having people who have access to more share. I think this really also needs a shift in, how we evaluate people for jobs. Because as usual, if we keep having, still the same metrics of how many papers, how many citations, how many first author works, this is not something that can encourage this type of collaboration that we so desperately need, and that will really enable more progress in science. So this is really something that is like for us senior people to take on, to really enable a change in the way we review job applications, so that like young and brilliant people such as all of you are actually able to spend time in this project and not thinking that they are in quotes wasting time or reducing their chances to find the job. So thank you so much. I have to say I had prepared this whole Slido quiz to force you people to interact. And you can say, like usually I teach undergrads. And so, I was very glad that instead I think we were able to have this really nice discussion. So I will instead stop here. And thanks again for participating.